DMA direct memory access is like a special helper that moves data from one place to another, without asking the main worker, the CPU, to do it step by step. The purpose is to let the CPU focus on other important jobs, while large blocks of data, for example a picture from a camera or a sound file from a microphone, are copied directly into memory. The architecture looks like this. CPU tells the DMA controller what to move: source address, destination address, and how many bytes. DMA controller, a tiny brain that talks to both the I/O device and the system bus. It takes the command, then temporarily grabs the bus reads from the device, writes to memory, and finally releases the bus. System bus, the road that data travels on, shared by CPU, memory, and peripherals. Think of the bus as a single-lane road. The DMA controller is a delivery truck that can temporarily close the lane, deliver a package, and then open the lane again for other cars, the CPU. This reduces the amount of time the CPU spends moving data itself, which speeds up the whole system. In cycle stealing mode, the DMA controller sneaks onto the bus for only one clock cycle at a time, then steps back so the CPU can use the bus in the next cycle. Operation. CPU sets up the DMA transfer, addresses, and count. When the DMA controller needs to move a byte, it asks the bus arbiter for permission. The arbiter grants the bus for a single bus cycle, a short steal. DMA reads a byte from the input-output device and writes it to memory in that same cycle. The bus is given back to the CPU for the next cycle. The process repeats until all bytes are moved. Timing diagram textual. CPU cycles: a series of 8 blocks representing clock cycles. DMA steal: caret symbols positioned under some of the CPU cycles, indicating a single cycle where DMA owns the bus. Each caret marks a single cycle where DMA owns the bus. The CPU works in the gaps. Bus arbitration works like a playground turn-taking system. The CPU normally has the turn, but the DMA controller raises its hand each time it wants a quick turn. The arbiter, the playground supervisor, lets the DMA take the turn for one beat, then returns the turn to the CPU. This way both can share the same road without crashing. In burst mode transfer, the DMA controller grabs the bus for a continuous block of cycles called a burst, and moves many bytes in a row before giving the bus back to the CPU. One CPU programs the DMA with start address, end address, and burst length, how many bytes per burst. 2 DMA asks the arbiter for the bus and receives a grant for several back-to-back cycles. 3 During the burst, DMA repeatedly reads from the I/O device and writes to memory each cycle like a fast train that does not stop at every station. 4 After the burst length is reached or the transfer is finished, DMA releases the bus and the CPU resumes its work. Timing diagram textual. CPU cycles a long bar of dashes. DMA burst shows 3 groups of 8 equals separated by spaces, each group followed by a caret line of 6 carets underneath. Each block of equals represents a burst of several cycles, for example 4 or 8, where DMA owns the bus continuously. Throughput characteristics. Because the bus is held for many cycles in a row, the overhead of requesting the bus each time is eliminated, so the effective data rate approaches the maximum bus bandwidth. If the bus can transfer 100 megabytes per second, a burst of 8 cycles can deliver almost 100 megabytes per second, while cycle stealing might only achieve about 50% of that because half the cycles are used by the CPU. Imagine a water pipe. Cycle stealing is like opening the valve for a second, closing it, then opening again. Burst mode is opening the valve and keeping it fully open for a longer period, letting more water flow at once. Latency is how long a single piece of data has to wait before it moves. In cycle stealing, each byte must wait for the next free CPU cycle, so latency can be as high as 1 full CPU cycle for every byte. In burst mode, the latency for the first byte of a burst is similar, but the following bytes arrive back to back with almost no extra wait. Bandwidth, bytes per second, is higher in burst mode because the bus is used continuously for many cycles. Cycle stealing typically achieves only about 30 to 60% of the bus maximum, depending on how often the CPU needs the bus. CPU impact. Cycle stealing The CPU loses one bus cycle for each byte transferred, which can slow down its own computation, especially in tight loops. Burst mode, the CPU loses a whole chunk of cycles, the burst length. If the burst is short, the CPU impact is brief. If the burst is long, the CPU may be paused for a noticeable time. A child-friendly picture. Think of a classroom where the teacher, CPU, talks most of the time. Cycle stealing is like a student, DMA, asking the teacher to pause every few seconds to read a note. Burst mode is the student asking the teacher to stop the lecture for a longer block of time to hand over a stack of notes all at once. The teacher loses less overall time with burst mode if the stack is large, but the pause feels longer in the moment. Explanation: let B be the bus width bits, and F the bus clock frequency hertz. The theoretical maximum bus throughput T max equals B times F bits per second. Cycle stealing transfer rate. Suppose the CPU uses the bus for a fraction alpha of the cycles, 0 less than or equal to alpha less than or equal to 1. The DMA gets the remaining fraction 1 minus alpha. If each DMA transfer moves W bits per cycle, usually equal to B, the average DMA transfer rate RCS equals 1 minus alpha times T max. For a simple case where the CPU needs one bus cycle for every instruction, alpha approximately 0.5, the DMA rate becomes about 0.5 times T max. Burst mode transfer rate. Let the burst length be L cycles. During a burst, DMA occupies the bus for L cycles, then the CPU may take C cycles before the next burst. The duty cycle for DMA is D equals L divided by L plus C. The average DMA rate RB equals D times T max. If we choose L equals 8 and C equals 2, then D equals 8 divided by 10 equals 0.8. So RB is approximately 0.8 times T max, a big improvement over cycle stealing. Bus utilization. Cycle stealing utilization equals alpha CPU plus 1 minus alpha DMA equals 1. Always fully utilized but split. Burst mode utilization equals L plus C divided by L plus C equals 1 during the combined period, but idle cycles can appear if C is large. These simple formulas help system designers estimate how much of the bus bandwidth each method will consume. Mathematically, the total time T total to move n bytes, where each byte equals W bits, in cycle stealing is T total CS equals N divided by RCS equals N divided by open bracket 1 minus alpha times T max close bracket. In burst mode, assuming whole bursts, number of bursts equals ceiling of N divided by L times W. T total B equals number of bursts times L plus C divided by F. These equations show that larger L longer bursts reduces total transfer time. How fast does the data need to move? If the device streams video many megabytes per second, burst mode is usually chosen to get high bandwidth. Can the CPU afford to lose many cycles at once? Real-time control loops, for example motor control, may need the CPU to run continuously. Cycle stealing, which only steals a single cycle at a time, is gentler on the CPU. What kind of device is talking to memory? Slow peripherals like keyboards produce a few bytes every second, so cycle stealing is fine. Fast devices like SSDs, network cards, or graphics GPUs benefit from burst mode. Are there strict timing deadlines? In hard real-time systems, airplane control, you often prefer predictable, evenly spaced steals rather than long bursts that could delay a critical CPU task. What is the bus architecture? Some modern buses, PCIe, AXI, support multi-beat bursts native, making burst DMA cheap. Older buses, ISA, may only allow short steals. A child analogy. Imagine you are sharing a playground slide with a friend. If you only let your friend use the slide for a second at a time, cycle stealing, everyone gets a turn quickly but slowly. If you let your friend have the slide for a longer stretch, burst, they zip down many times before you get it back, which is faster for them but you wait longer. So the selection balances speed, burst, versus smoothness, cycle stealing, and the urgency of the CPU's own work. Controller configuration. Most DMA controllers have registers that hold the source address, destination address, transfer count, and mode bit steal versus burst. Setting these correctly is like entering the correct street address and how many letters to deliver. Buffering. Some DMA engines use an internal FIFO first-in first-out buffer to smooth out the data flow, especially in burst mode. This prevents the device from stalling if the memory side is temporarily busy. Error handling. If a transfer fails, for example memory parity error or device not ready, the DMA controller raises an interrupt. The operating system can then retry or abort. Think of it as the delivery truck pulling over and ringing the bell if the mailbox is locked. Cache coherency. In systems with CPU caches, data written by DMA may sit in memory while the CPU still holds an old copy in its cache. Software must flush or invalidate the relevant cache lines before and after the transfer. This is like telling the teacher to erase the old chalkboard notes before the new ones are written. Interrupt versus polling. After finishing, DMA can either send an interrupt, the teacher calls the class to say delivery done, or the CPU can poll a status register, the teacher keeps checking the mailbox. Interrupts are more efficient for large transfers. Security. Modern DMA must respect IOMMU input-output memory management unit mappings, so a device cannot write to arbitrary memory. This is akin to giving each delivery truck a map that only shows authorized houses. Case Study 1. Modern PC graphics. A GPU needs to move texture data hundreds of megabytes from system RAM to its own VRAM. The driver programs the PCIe DMA engine in burst mode with a burst length of 128 beats, achieving close to 16 gigabytes per second PCIe 4.0 bandwidth. The CPU is only briefly paused, allowing games to keep high frame rates. Case Study 2. Embedded microcontroller with UART. An ARM Cortex-M microcontroller receives sensor data over a UART at 115.2 kilobits per second. The DMA is set to cycle stealing mode so that every received byte briefly steals the bus, leaving the CPU free to run a control loop every 1 millisecond. Measured throughput is about 90% of the UART rate, and the CPU utilization drops from 30% to under 5%. Benchmark numbers illustrative. Desktop PC, PCIe 4, burst mode 128, transfer size 256 megabytes, observed throughput 15.8 gigabytes per second, about 98% of maximum, CPU load less than 2%, brief stalls. Embedded Linux, Ethernet, burst mode 32, transfer size 10 megabytes, observed throughput 950 megabytes per second, about 90% of 1 gigabyte per second, CPU load around 10%, short bursts. Microcontroller unit, UART, cycle steal mode, transfer size 1 kilobyte, observed throughput 110 kilobits per second, about 95% of UART, CPU load less than 1%, continuous steals. Microcontroller unit, SPI flash, cycle steal mode, transfer size 512 kilobytes, observed throughput 12 megabits per second, about 80% of SPI, CPU load 5%. These examples show that burst mode shines when the bus can handle long, uninterrupted transfers, and the CPU can tolerate short pauses, while cycle stealing is preferred for slower peripherals or hard real-time CPUs that cannot afford long pauses. Overall, understanding when and how to use each DMA mode lets designers build systems that are both fast and reliable, just like choosing the right way to share a road between delivery trucks and regular cars.